All right, let's dive in. Today, we're not just going through a science lesson, we're cracking a detective case. The mystery? The atom itself. For decades, it was this huge puzzle, full of really strange clues, shocking twists, and some absolutely brilliant deductions. And our story starts with a clue that honestly seems to defy all common sense. And yeah, that's the big one. It's a scientific fact that the atoms making up your hand and the desk you might be sitting at are almost entirely empty space. So, why do they feel solid? Why can't you just push your hand right through it? This is the core mystery that scientists had to solve, and believe me, the answer completely changed how we see reality. To even start to solve this, we have to rewind the clock to the early 1900s. Back then, scientists had their first real working theory of the atom. It was simple, it was logical, and as we're about to see, it was completely wrong. They called it the plum pudding model. Just imagine a big, fluffy, positively charged cloud, like a pudding. And then you have these tiny, negatively charged electrons just dotted all throughout, kind of like raisins or plums. Think of it as a snowball with little bits of sand scattered inside. It made a certain kind of sense, and for a while, it was the best idea anyone had. But of course, a great theory needs a great test. And this is where our story gets a major plot twist, all thanks to a scientist named Ernest Rutherford. He set up what he thought was going to be a pretty routine experiment, really just to confirm the old plum pudding model. Instead, he blew the whole case wide open. So here was the plan. You fire these tiny, positively charged bullets, they're called alpha particles, at a super, super thin sheet of gold foil. Now, if the plum pudding model was right, the gold atoms would be like those soft snowballs we talked about. The alpha particles, they should just sail right on through, maybe getting nudged a tiny bit, but that's it. But that is not what happened. Not even close. The results were so unexpected, so completely against the theory, that they were described as, well, a complete and total surprise. This was one of those moments in science where everything you thought you knew gets thrown right out the window. And this is what they saw. Yeah, most of the alpha particles did go straight through, just like they predicted. But then, a very, very small number, were deflected at these huge angles. And some, incredibly, bounced almost straight back, as if they'd hit a tiny solid wall. Rutherford himself said it was as incredible as if you fired a 15-inch cannon shell at a piece of tissue paper, and it came back and hit you. So this bizarre result created a massive puzzle. What in the world could be inside that atom that was dense enough to repel an alpha particle like that? Rutherford came up with a revolutionary answer, one that would completely redefine the modern atom. He realized the plum pudding model had to be wrong. An atom wasn't a soft snowball at all. Nope. Instead, he proposed that it's mostly empty space, with nearly all of its mass and all of its positive charge crammed into an unbelievably tiny, dense center, the nucleus. So most alpha particles just flew through all that empty space and missed the core entirely. But the few that scored a direct hit, they got repelled and bounced right back. And this brand new model revealed the star of the show inside that nucleus, the proton. It's a positively charged particle, and here's the kicker. The number of protons in a nucleus is what makes an element what it is. Got 6 protons? You got carbon. Got 11? That's sodium. It's that simple. And that counts. That number of protons has a special name, the atomic number, which we represent with the letter Z. You can really think of it as the atom's unique fingerprint. Every single element on the periodic table has its own atomic number. It's their ID. But protons aren't in the nucleus all by themselves. They're joined by neutrons, which, as the name suggests, have no charge. And the total count of these particles, protons plus neutrons, gives us what we call the mass number, or A. And since these particles make up pretty much all the atom's mass, we give them a group name, nucleons. Okay, so let's just put it all together real quick. You've got positive protons and neutral neutrons, both packed super tightly into the nucleus. And then you have the tiny negative electrons orbiting that nucleus way out in all that vast empty space. This is the new picture of the atom that came out of Rutherford's incredible experiment. But just when our detectives thought they'd finally solved the case, a new, even deeper crisis popped up. It turns out that according to the laws of physics at the time, Rutherford's own amazing model had a fatal flaw. So here's the problem. The laws of physics back then were crystal clear. A charged particle, like an electron, when it's moving in a circle, should act like a tiny radio tower. It should constantly be broadcasting away its energy. And as it loses energy, it would slow down, its orbit would decay, and it would go spiraling right into the nucleus in less than a second. This led to a really terrifying question. I mean, if the rules of physics were correct, then every single atom in the entire universe should instantly collapse. Nothing should exist. So why are we here? Why is your desk still solid? Why is matter stable at all? The case was definitely not closed. The hero who swooped in to save the atom from this theoretical collapse was a Danish physicist named Niels Bohr, and he proposed a truly radical idea that basically bent the known rules of physics and introduced the world to the super weird logic of the quantum realm. Bohr's brilliant solution was to just say, hey, maybe the old rules simply don't apply inside an atom. He proposed that electrons can't just orbit anywhere they want. They can only exist in these special quantized energy levels or orbits. Think of it like a ladder. An electron can stand on one rung or another rung, but it can never ever float in between the rungs. And as long as it stays on one of those stable rungs, it just doesn't radiate energy. And just like that, the world of quantum mechanics was born. And get this revolutionary model didn't just solve the stability problem. It also perfectly explained another huge long-standing puzzle: why heated elements only emit light at very specific colors or frequencies. Well, those specific frequencies perfectly match the energy released when an electron makes a quantum leap down from one specific rung on the ladder to a lower one. It was an absolutely huge breakthrough. So Bohr's model saved the atom from total collapse and really cemented this picture of a tiny, dense nucleus. And with this new, stable foundation, scientists could start digging even deeper into the nucleus itself. And what they found was that it wasn't always the same. This led them right to the discovery of isotopes. A classic example here is carbon. Okay, so both carbon-12 and carbon-14 are absolutely carbon atoms. Why? Because they both have 6 protons. That's the rule. But carbon-12 has 6 neutrons, while carbon-14 has 8. Now, they behave identically in chemical reactions, but that difference in neutron count gives them different physical properties, like making carbon-14 radioactive, which is the secret behind carbon dating. And so the great atomic mystery started to unravel, from a simple pudding to a tiny solar system held together by bizarre quantum rules. But the detective story of science, well, it never really ends. Bohr's model wasn't the final word. It was just the first chapter in a radical new story called quantum mechanics. It opened up this whole new world of questions, which really just leaves us to wonder, what deeper puzzles about the very nature of matter are we still trying to solve right now?